Okay, so where are we? We're talking about supervised learning, and we're talking specifically about classification problems where we predict a class label based on the other attributes. And so we gave an example of predicting whether or not we play some sport based on a few different attributes representing the weather, or predicting whether a passenger aboard the Titanic did or did not survive based on things like their gender, their age, the fare they paid, and so on. Okay, and so to get started here, we talked about just manually guessing simple rules that might explain the data, and as you might imagine, the relationships between the attributes and the class label are complex, and so your intuition may be wrong, and so you need some way to automate the search for these kinds of rules. Okay. So we talked about this one rule algorithm that will proceduralize the process of choosing a good rule, and that worked fine. But obviously it's pretty limited, right? It can only find very simple kinds of relationships. And so we also talked about a sequential cover algorithm that builds up sets of rules that may have multiple conditions in them. Okay. So great. So a set of rules that are themselves complex are more descriptive of the data and therefore have better strength as a classifier, but they're also harder to interpret. And one of the points that we've been making in this class is that communicability of these models, communicability of the results is important. Okay, and so a single rule is easy, a set of complex rules is perhaps less so. And for that reason and for other reasons, we can talk about decision trees. And we sort of showed that a decision tree, I was about to say, can be constructed from a set of rules. Each path from the root is a rule, but that's not quite true. Constructing a decision tree from a set of rules is not necessarily trivial. Going the other direction is straightforward, as we described. Every path from the root is a rule. Okay, but there is a relationship. Moreover, given a decision tree, it's pretty easy to interpret, I would claim, right? You just sort of take your data item and look at the root node and answer the question. Is the gender male or female? Female will then go down this branch, male go down this branch. So it's very easy to understand what's going on. It's also easy to understand what the most important decisions are because they bubble up to the top. Okay, and so if someone's asking you, well, why, how is your model behaving? Why does it make one decision over another? You can sort of answer those questions. Okay, and so we talked about using how you make the decision of which attributes to select at each level, and we talked about entropy being a measure of sort of the purity, right? The game is to try to make an entire branch pure with respect to a class label, right? Everyone down this branch survived. Okay, and so entropy gave us a way to do that. And then we talked about a few extensions for numeric attributes where you could split based on at a particular level, as opposed to I said if you don't have gender, male and female, but rather you have a number like humidity or the fare they paid, you have to be a little more careful. You don't want to have 1,000 different branches coming out of a node, one for each unique value. Rather, you want to bucket them somehow. And so what's the way to bucket them? Well, one idea is just to find a split point that splits into two children. So everything below this value goes one way and everything above this value goes another way. And we talked about how to find that threshold. Okay, so fine. So where we are now is that decision trees are potentially prone to overfitting. And so let's talk about that. This excerpt is from Pedro Domingo's 2012 CACM paper that we've mentioned before. So, what if the knowledge and data we have are not sufficient to completely determine the correct classifier? So it could be that we've, designed a classifier that is responding to what, he calls random quirks in the data as opposed to sort of uncovering some kind of fundamental truth. It doesn't have any predictive power in the real world. It just sort of describes this particular data set. And so the problem here is overfitting. And, he says it's the bugbear of machine learning. A lot of machine learning problems really reduce to how do we avoid overfitting, right? Because you can always train a model on a particular data set, but how do you avoid specializing it to this data set and making sure it has some predictive power in the real world? Okay, and so the case to look out for here is when your learner outputs a classifier that is 100% accurate on the training data but only 50% accurate on test data, when in fact it could have output one that is 75% accurate on both, it has overfit. Okay, and so I want to call out that this is really the definition to think of when you think about overfitting. Low error on training data and high error on test data. Okay, so an image that sometimes is called to mind when you're talking about overfitting is this one, which is, I've fit two polynomials to a small set of data points, one with a high degree, I think 10, and the other with a low degree, in this case, actually it's still pretty high, it's 5. And you can sort of see that a couple things. One is that the red curve is exactly matching the data, okay? But you can also see that the sort of what appears to be the trend in the data probably is better described by the green line. And in fact, it was generated by a model that's sort of adding some random noise to a curve, and so the green one probably does actually reflect the actual underlying data model, the underlying process which generated the data. But the other point to look out for here is it's sensitive to changes, to perturbations in the data. If I move one of these points, just one of these points a little bit, how much does that curve change? And the green one would not change much, while the red one might. Okay, but I actually don't think this curve fitting model is the best image to call up when you think about overfitting, because it's in my mind it's a little bit specific to polynomial curves and the number of degrees of freedom you're working with. Okay, so it's not always clear, at least to me, how to map this image that I call up in my head of overfitting to machine learning problems. So I think a more useful one is one that's actually associated with a Wikipedia page on an article related to overfitting that's released under Creative Commons, is this, that over time your error goes down for both your training set and your test set, but at some point it continues to go down for your training set. I'm pointing at the wrong screen. This continues to go down on your training set, but then it starts to creep up on your test set. And so at this point, he's put a little symbol here to indicate that's where overfitting has set in. And so I think this is the image you should call to mind when you're thinking about overfitting problems, is this difference between the error on your training set and the error on a test set. Now, in some cases it's tough because the test set, may be, what is the test set? Is it something you actually have your hands on where you can measure this error, or is it more like the predictive power in the real world? But regardless, any kind of estimate you have over the error that you're actually achieving on data that you didn't train on is what to look out for. And when these start to diverge, that means you overfit. All right. So, other language to be familiar with around this concept, is the model able to generalize? That's when you're, if it is able to generalize, then you are not overfit. Okay. Can it deal with unseen data, or does it overfit the data? Test on. So in order to solve for this, you test on holdout data. Okay, so one way to do this is split the data to be modeled into training and test set, just in a fixed way. Train the model in the training set, evaluate the model in the training set, and then evaluate the model in the test set. And the difference between those two, again, is a measure of the model's ability to generalize. A measure of how overfit it is. Okay. Now, doing this just once, splitting between training and test, is not the most powerful mechanism to do this, and in a couple of slides give you a better one. All right. So another image to kind of call to mind when you're thinking about overfitting also comes from Pedro Domingo's paper, which is this distinction between bias and variance. So in the underfit case, right, you're missing the mark. You're not describing the data very well, but you might have low variance. You're clearly missing the mark. And then high bias and high variance, well, then you're sort of just way off the mark. You haven't, your learner is not producing anything useful at all. But in the overfit case, you might have very, very low bias, but you have high variance. Now, the way to interpret this language I'm using, the high variance, is variance when you add more data, or when you perturb the data, or when you evaluate on a different data set. What's your quality look like? Right? How well do you do? Okay. And so if you have low bias on your test set, but it's sensitive to the data, right? That's where the high variance comes from. Then you're in an overfit scenario. Okay. And in the other case, well, you're not very sensitive to the data. You have low variance, right? But you're biased, but you have high bias. You're wrong. You're getting the wrong answer. So this is like if I just have a model that's always predicting, let's say I have a model that says for the Titanic data set that everybody dies all the time. Well, this is very insensitive to the data, right? It has low variance, right? No matter what data set I give it, it always produces the same answer, but it has high bias. It's wrong, right? The error is high. While overfitting is the other way around. Maybe I'd get an exact answer on my training set where I have very, very low bias, but as soon as I add one more data point, it changes drastically. Okay, so this is another set of terms and kind of concepts to think about when you think about overfitting. All right.